planets. We need that here on the Earth. Actually, protecting all the planets, especially Earth and Mars. Her work focuses on the scientific, technical, legal, and societal issues of ensuring that missions to the Red Planet and other solar system bodies do not either inadvertently bring terrestrial microbes along, which would complicate our search for indigenous extraterrestrial life, or return any microbes to Earth. Recently, she's done a research study on the environmental impact reviews and public communication associated with high containment biosafety labs, the type that will eventually be used for the quarantine of returned samples from Mars. To Margaret's right is Oana Marcu. Research interests include molecular adaptations of cells to extreme habitats on Earth as analogs for Mars environments that could harbor life. Survival of life in deserts requires adaptation to desiccation, extreme temperatures, and radiation, which limit the presence of life. For extremophiles, adaptation implies maintaining the structural and functional integrity of biomolecules, DNA, proteins, lipids, etc., which are otherwise damaged through oxidation. And finally, I'm happy to introduce Dale Anderson. The exploration of the Antarctic continent readily conjures up images of desolation. But for humans to survive there, they must be members of carefully planned, integrated teams. As the American leader of the joint US-Soviet expedition to Antarctica, biologist Dale Anderson spent 6 months with a multinational, multicultural crew in this remote, hostile environment, carrying out research relevant to the search for life on Mars. He says, in addition to the rigors of the local environment, we had to address the challenges of our differing cultures and languages. So I'm very happy to turn the mic over to Margaret for a short 4 to 5 minute first thoughts, please.
Okay, well, most people are here because they're interested in aliens, and believe it or not, I'm a marine biologist. So when we think about aliens, and how I got into this whole business of astrobiology comes through thinking about introduced species. And so believe it or not, the Outer Space Treaty of 1967 and various environmental laws are what come into play, especially when we talk about bringing things back to Earth. So thinking about aliens is something we do all the time. Whenever you think about H1N1, whenever you think about emerging diseases, bioterrorism, nanotechnology, and synthetic biology, you're thinking about aliens. And so it makes sense to have people studying deserts and Antarctica, because whenever we go into a new location, a cave, think about Legionnaire's disease, all of these are microbes that could do us harm. Generally don't, but you need to be cautious. So planetary protection is what I work on, and it's not optional. It goes along with mission planning, and there's even a funny bumper sticker that the Planetary Protection Officer at NASA put together. All of the planets all of the time. Whenever we do a mission, we think about what could we be bringing along, that's forward contamination. How do we make sure that when we go to look for life on Mars or someplace else, that we don't bring it with us and then say, I've discovered it, only to find out it was from Cape Kennedy. And likewise, when we bring things back, NASA may be in control of civilian airspace or the European Space Agency or others who launch, but as soon as you come back to reentry, all of a sudden, Center for Disease Control is interested, or EPA, or Department of Interior, and that's just the United States. So we have real concern. Anybody who's gone to an airport and has been stopped by USDA who says, have you been on a farm? Do you have any fruits or vegetables? That's the same scientific concept we're talking about. So planetary protection is something that is very much ongoing. It draws from biology that all of us understand from either the newspapers or the textbooks. It gets a bit more complicated when we start talking about human missions, because all of us are carrying our own little assemblage of microbes with us. And so when we go there as human crew members, we would automatically be bringing microbes with us. Are those harmful contaminants or not? How do we think about these things? So behind the scenes, as the rocket scientists and astrobiology scientists are thinking about looking for life, there are people like myself who think about making sure that when we do it, we protect the science, we protect the planet when we go there or bring things back, and we protect our crew and people, including ourselves.
Thank you. Roanna?
Thanks, Margaret. I want to follow up a little bit on what Margaret mentioned, and it's this thought that we have a planet here and things somewhere else, and then there's deep space in between. And there are three things that come to mind, and actually the other half of my life is spent doing space biology, trying to understand how our life adapts to deep space. So the number one thing that comes from the hardcore science data, which basically says that the immune system of humans or other organisms is a little bit depressed in space. And there's also, we see it everywhere, there's an increase in virulence in microbes that are on our own planet. So this is not an extreme biology, it's not aliens. But how alien do we become, or how extreme do we become when we go into space? So that's one area of concern. And I don't know if I want to say just concern, it's basically an important area to study. The second one is the hardcore science data that we don't have. And that's actually the space biology or the biology in deep space. So all the data that we have comes pretty much from low Earth orbit. We have not done any biological experiment for long-term duration in deep space. So in fact, we don't know what happens. So again, that's an area of concern and where we need more data. And I think third, what's really important for me as a biologist, but also as a human being and thinking about our neighboring planet, is this social aspect of how do we treat other planets. And it comes down really to common sense and knowledge. And the common sense is when you go to your neighbor, what you do is you don't just barge in and say it's yours. What you do is call ahead of time, knock on the door, wipe your feet, and should the culture be like that, you take your shoes off. So I think it just comes down to common sense and good neighborhood rules. And the other aspect of the social aspect is how much do we fear these, infections or interactions with aliens or other forms of life? And I think that's really important because as humans, we live in a circle of possibilities. And one of them, of course, is the possibility that something bad might happen. But what I like to keep in mind as a scientist in this world of possibilities, that the universe is actually really friendly as well. That's one of the possibilities as well, right? So if I think of the long term, and I would be very happy if we find biology or aliens in my lifetime, but I think what's really important are these three things. One is to learn as much as we can until we get there, and that's really, really important. And the reason it's important is because it allows us to do two things. One, to not be reckless when we go there, or when they come here, and two, is not to actually fear it. So you have to take a step forward out of the best knowledge you have, and just kind of hope for the best interaction.
Well, I guess most of my work over the years has been looking at life in extreme environments and trying to characterize those environments and understanding how those microorganisms exploit the places that they live. And then we try to extrapolate from there to provide us lessons with what might we expect on Mars and how can we think outside the box sometimes. So it's, just to give you an example, if we have a planetary spacecraft that goes to Mars and it's got an RTG, a radio thermal device on it, something that provides heat that's then turned into electricity. If that happened to crash into the planet in an area where there's a lot of ice-rich ground, it could actually provide a heat source that would then provide liquid water in that little micro niche, and you might contaminate the soil with the organisms that are still bound to the spacecraft, or if there's microorganisms that are naturally occurring that's locked up in that permafrost, if they've survived, it could provide an environment where they would be growing. So it's those kind of issues that we have to keep in the back of our mind when we're doing our work, both in places like the Antarctic, where we're also trying not to forward contaminate those areas, or lakes, for example, Lake Vostok, underneath the thick ice, and then trying to feed into people like Margaret, who are the policymakers, and trying to understand how we can go about protecting both the Martian environment or the outer planetary moons, and then of course the return of materials back to Earth. Well, let's just take it from there.
Thank you. As the moderator, I'll ask the first question. I remember distinctly with the first Apollo missions, the astronauts were put in quarantine for, I don't remember how long, but they were put in quarantine. And fairly soon after that, that was eliminated, that step was eliminated. So I'm asking what was the human story that actually made that happen?
Okay, when we thought we would have a sample return in 2007 is when I got involved. And so in the late 1990s, we began asking questions. What would we do if we got the rocks tomorrow? Sample return from Mars. And so the first thing we did was look back at Apollo. What did they do when they went to the moon? We in the Bay Area have a chance to actually go into a quarantine module. One of the quarantine modules for Apollo 14 is actually on the USS Hornet up in Alameda. You can go onto it. So what they did is they had Airstream trailers, the kind of, like a regular vacation trailer, and they specially sealed it up, and those became quarantine modules for the astronauts. I can tell you now that if there were life on the moon, we would have it here on Earth, because everything we did, no matter how comprehensive the protocol was, that was the late 60s. We didn't understand microbes the way we do now. We didn't have the technology that we do now. We didn't have the resolution to see down to small scale. In addition, the laws were different. There was, at the time that Apollo launched, they said if the astronauts were contaminated, they would be quarantined. And there was a constitutional question there about whether or not whether NASA could do that, because it wasn't an agency that had statutory law. So they said that you can't, that's a taking of freedom. It's a constitutional issue, so NASA couldn't do that. And they also said they published that in the Federal Register as a quarantine regulation on the morning of the launch in order that there wouldn't be too much comment on it. You couldn't do that now. The laws, the environmental impact laws, the public is different. We know how to watch the government for decision making. So all of what we learned in Apollo was very, very good, and we started to build on that. And we brought the laws forward, we brought the science forward, and in a nutshell, we have a very strong protocol. So we developed a draft protocol in 2002 that said if we get rocks from Mars, we'll put them into a BSL-4, Biosafety Level 4 glove containment box and lab, which has never been built yet. We would take them through a series of tests. There would be people involved in making decisions about when they would come out. And actually, the Apollo rocks were kept in quarantine a lot longer than you think. So the astronauts went through a quick quarantine, but the rocks themselves, some 800 pounds of them, are still very much in a quarantine. Now the quarantine is for planetary containment, to keep the rocks nice and safe so they're not contaminated with Earth things. But we did Apollo 11, 12, and 14 were all done with this strict containment. At that time, we had enough studies that said there's no life on Mars, so then it's just a matter of protecting on the moon. So it's just a matter of protecting the samples, not us from the samples. So we're constantly, so really this whole idea of planetary protection from aliens is the same kind of work that goes on within the public health community. And we do learn from our mistakes. And Apollo was a very good effort for the time, and it wouldn't be good enough now.
Margaret, just one quick question for you, because I don't remember the details, but quarantine was broken very quickly on the Apollo returns, as I recall.
How so?
I think they opened up the trailer and let people in.
No, okay, so if you look at pictures, so he's saying that they opened up the trailer and let people in. What it was is the original plan was that the Apollo capsule would come down, land in the water, and be lifted onto the aircraft carrier. And if you remember the movie E.T., and it had that sort of clear plastic tunnel that went, okay? Well, that was actually the Apollo, if you look at some of the Apollo drawings. And so they were supposed to get out of the capsule and go right into this module. It turned out the seas were too rough, the crane wasn't strong enough, and so what they did is they let the capsule land in the water. Navy SEAL divers jumped out of the helicopter and threw in, so they did pop the hatch. And they
Right.
actually popped the
Right.
hatch up higher when they first came into the atmosphere. So that was one of the breaches. Another one when they opened up. But the astronauts, when they walked across the deck of the ship, they were wearing what were called BIGs, biological isolation gear. They actually had respirators on. And so nothing was getting out. And then they went right into those quarantine modules. And so it wasn't really broken in the sense, if I run from here to there, am I going to contaminate you with smallpox? I don't know. So it's that kind of thing. It was a decent contamination control, a good quarantine. Was it perfect? No. But it wasn't broken that was not really a break as much as you'd think.
Right.
Although when they were done with the caps, all of the flotation devices and everything around the capsule, and the astronauts and the capsule were on the ship, they sank all the leftovers, so it's already in the ocean. So see, there's things like that you wouldn't do now.
Right. In comparison to a return from Mars, those protocols wouldn't even come close. I mean, half the time
That's
we
right.
talk about keeping people in orbit and trying to figure out what we're going to do with them if they've been contaminated.
Yeah.
So it's a much different issue.
And so when I was involved in some of the early discussions too, they said, let's get together one of the technologists. This guy was fantastic because they said, okay, tell me what I need to do to keep this stuff in, because the National Academy had done a study and said, first thing you want to do is seal it and contain it, and don't break containment until you get it into a glove box. Okay, what does it mean to seal and contain it when you don't know what the life would be? So they said, give me some size. What's the pore size of this stuff? What's the filters I use? And so finally he said, oh, you guys are no good. The biologists were no good giving him information because we don't know what the life is like or how big it was. And if you remember, that was around the same time we were arguing whether the meteorite had life in it, whether that was too small to be something that was living. And so he says, how about if I design it so a methane molecule can't get through? So he said, good idea. So he goes away, and he comes back, and he's got this thing that looked like a soccer ball. And he said, okay, so this is an OZ, an orbiting system. And what it was, you collect the materials on Mars, the rocks and pebbles and dust. You put it in here. It pyro welds automatically up there. Okay, so it's welded shut. Made of a metal, can't get through, methane molecule can't get through. And so he said, so this is an orbiting system, this can come, we can monitor, make sure no gases are coming out when we're coming back, we can monitor as soon as we land on Earth, nothing's getting out. And so one of the scientists said, that's great. Now the first thing I want to do is get at the head gas on the inside. So now we've got all of these mixed samples on the inside, so what's the gas that's in there? I want to get that before it gets too warmed or contaminated by anything else. And so he says, that's the first thing I want to do is open that. And the guy says, I'm not a scientist, I'm not an engineer, I'm a technologist. You asked me to make something that won't leak. I did. He said, it's like you asked me to make a Coke can. I did. Now you're asking for the pop top. It's a different project. So it's a fascinating mix of working. So I get to work with rocket scientists, I get to work with technologists, and all of the thinking about infection, about what we know on Earth, about what might be on Mars, then goes into being turned into something like, okay, then how do you turn that into a standard? How do you turn it into an engineering and design constraint? And then how do you then talk to the public about it? So it's been a great journey, and as a marine biologist who worked on mud snails in San Francisco Bay that came in on the Transcontinental Railroad, I never thought I'd be working on something like this. You never know where your education will take you either.
I think that kind of points out a little bit of the tension that's between scientists that want to do the work and having to return samples and having to face policy people and the regulations that are going to keep you from doing that work. So how do you go about doing what you want to do? I mean, how long do you have to stay in quarantine, for example, when you bring something back? What kind of a facility does it have to come into before you're allowed to get to it? And how do you protect the integrity of that sample? Because some of the folks that want to do the planetary protection might want to sterilize it, for example, make it heat treated so that it kills everything in there. And of course, if you do that, it destroys your sample, or it destroys the integrity of the sample. So your learning curve might go way down.
Yeah.
So it's a complicated and convoluted set of arguments that you have to deal with.
Well, the thing is, it's like if you wanted to add an addition to your house, you'd go and check with your county about what the zoning is and what the requirements are for permits on your house and things. So where do you go to for these kind of permits? They don't exist. So all you can do is build on what we know. And everything we've done is life as we know it. And the assumption is that first. And that's why we do work in deserts. We do work in Antarctica and the Arctic. We go into deep caves. And actually the desert, yours is probably the safest work out in the desert, because while we're looking for things that can withstand radiation and really dry conditions, those tend not to be the ones that we have to worry about. When we've got nice moist conditions inside of our lungs, warm, nutrient-rich, and moist, those are the ones that maybe are more concerned to us. But we're equally concerned about things that might affect our ecosphere, you know, all the ecosystems that are out there. So it isn't just the organisms that are, we're very human focused, but we're thinking about other things as well. And so each of these laws, regulations, policies gets made up one layer at a time and challenged at every step. And so this is really Civics 101. This is how do you take science and use it in a democracy? So I talk to students a lot about that too, because it takes way more than just scientists. It takes a good science fiction writer, it takes lawyers, it takes engineers, technologists, people that design spacesuits. It's all sorts of really neat jobs that are part of NASA and our expansion and exploration elsewhere.
I have a question that I think I'm going to direct first to Oana, so you can speak a little bit. You have heard of a lot of people being afraid that a mini black hole would be formed at CERN, or before that at Brookhaven, and that it would swallow up the Earth and all that. In fact, there were even some lawsuits brought to stop this project at the LHC in Geneva. Now, nature happens to do this experiment almost every day by shooting actually much higher energy particles to our atmosphere, creating whatever regime that exists within the LHC. And so far, no black hole has devoured the Earth. So we have nature giving us an example. Now, I am going to use that as a simile and ask you, what are your feelings about or thoughts about panspermia? Is it possible to have a virus or a life form come from another planet? We know that meteorites arrive from the moon, from Mars, on Earth. Is it possible to have something survive, since that's your specialty?
Yeah, that's a really neat question. In fact, there's a lot of room for debating there, since we have no record fossil that goes so far back in the history of Earth. There's room for these speculations that our own life might have come from panspermia. And there are, in fact, some space biology experiments that have sent meteorites in space just to test whether life could survive, for example, encased within a rock. So, and yes, there is survival, for example, for really hardy things like lichens or things like that. And that's actually the whole idea. The way I like to think about it is that, yes, we find that it also extends into where would we look for life elsewhere. So in Mars, for example, you could look for life that's protected from radiation or from pressure from entry into the atmosphere within a rock, for example. Really high energy radiation and panspermia. You know, the good news about it is that if panspermia did happen and it's part of the origin of life on our own planet, well, we're here, right? So it's actually not so bad. There's also theories that say that maybe comets, ice comets would have transported life and so on. So, you know, it comes down to experiments. It's very interesting that you brought up the CERN, because in fact I work at the Stanford Linear Accelerator Center, and we do biology. In the past 10 years we started doing biology there as well, but looking at fixed tissues. So just last year we did this experiment. We work with these organisms in the desert that are very, very resistant to radiation. And what I wanted to do was to really look at cells live. So what we look is these elemental fluctuations that happen in the cell in response to the environment. So the thought was, well, you hit these cells with 10 keV of synchrotron radiation, they'll die. The thought that came after that was, well, they're extremophiles, they should resist some radiation. So in fact, we did that experiment. We built a chamber, we put it in a humidity chamber, we put the live cells, and we hit them with synchrotron radiation. And they survived for about 5 hours under the beam and were able to do this experiment. So it was a fascinating experiment, but you also had to take the leap of faith and learn or use what you've learned already, that they are very resistant. And basically it was the leap of faith was just say, I'm going to do this experiment and see what happens. And see what happens. In fact, it's incredibly informative, both biologically as well as in terms of what life can withstand and how many mechanisms we have of resisting radiation and all sorts of other things. And that there are ways that we can cope with this high radiation environment or high really stress environment.
Do you have some thoughts about putting things in perspective with your work versus the natural occurrence of transference of life?
For me or for
No,
Margaret?
Elizabeth.
For Margaret.
Yeah.
Oh, for me?
Yeah.
Oh, okay. Well, there was a study at one point, so everyone was talking about Mars sample return, and NASA asked the National Academy of Sciences to take a look at, well, what if we wanted to return samples from someplace else? Should they be contained at the high level of containment we're talking about for Mars? And they took up that question, does every place where you bring a sample back require the same kind of stringent controls? And the answer is no. There's some places where we think not. And obviously what they did was looked also at how long have they been out there? When a rock or a comet or something is coming in, it's been out in space for a very, very long time. When we're bringing it back, we're bringing it back deliberately within 1 year, fully contained. And so if there's anything in it, it could really still be alive. Could something be alive for a very long time? And so the questions at that time actually didn't have the data that you're talking about. And they were saying, how long could a spore stay in a dormant state and be exposed to radiation of the sort that could break DNA bonds? Or does it have to activate and then repair those bonds and then go back into a dormant state? So they looked at it that way and said, if you've been out there in space and you can't reactivate and become a replicating organism and repair DNA breaks, after about 35, 40,000 years, you probably can't make it anymore. So we're just taking life as we know it, thinking about the extremes that we find, and say what's the probability of this panspermia idea, the idea that life may have come to Earth by being seeded from the outside. It's still a very viable hypothesis. We don't have the data for it, but we want to keep that as one of the things in mind. But life in some forms, not us, but microbes that can go into a dormant state are very, very impressively hardy. Yes?
Right, and I would say that one of the lessons that we've taken from regions of permafrost, in Siberia you have some of the thickest permafrost layers in the world, upward of about 300 meters or so or more. And in the late 90s, Chris McKay, myself, Emery Friedman, and David Gilachinski were working there, and part of that work involved drilling into the permafrost and sampling it. Some of these units were about 3.5 million years, and Emery could pull some of these sediments out and reactivate the bacteria that were located in those sediments. So the question came up, how much of a radiation dose are they acquiring during that stay underground locked up in the sediments? And so Chris and I took a radiation detector with us, and we measured the background radiation and then came back and did the calculations, sort of back of the envelope rough calculations to see what they were exposed to. And the take-home message was that they could probably survive for millions and tens of millions of years, but once you started getting into the hundreds of millions to billions of years, as Margaret was pointing out, they've probably had so many holes punched in them that they can't repair themselves to replicate later. So it does put some limitations on survival through long distances. But I think another interesting part of this whole discussion, though, is planetary spit swapping, and it comes back to the origins of life here on our planet and the origins of life perhaps on Mars. Because if planetary conditions were more favorable early on early Mars, maybe that's where the origins of life took place, and pieces of Mars seeded life here, or vice versa. So I think one of the cool questions that's out there is when we do get to Mars and get to study it in greater depth, are we going to find that we find ourselves? Is it just going to be life that's like us, or are we going to find a completely separate tree of life if we do indeed find life there on that planet?
So the Garden of Eden could be on Mars. I'd like to open the floor for questions from the audience. We have 2 microphones on the aisle if you would like to stand up. Could you do a very short introduction or give us your name and address your question to one or all the panel? Thank you.
My name is Gary, pardon my hoarse voice. So speaking of Mars, can one of the panelists give us a quick overview of the level of protection that was taken for the Mars Science Laboratory?
Sure. The
MSL.
level, so the question was, can it give you an idea of the level of protection taken for the Mars Science Lab? Mars Science Lab is the one that's on the way now that will land in August on Mars, and it's a rover the size of a Mini Cooper car. So it'll go for, if we thought Spirit and Opportunity were long-lived rovers, this one will presumably go even longer. So like anything else going to Mars that's going to land, and in this case dig in the surface, it goes through Planetary Protection oversight within the Office of Planetary Protection. So all of the parts as they were being put together were sterilized and cleaned. We have an indication of all of the organics that are on it. Any of the pieces that will touch the surface, including the wheels, are especially cleaned. Inside, the embedded burden inside of the spacecraft parts, those don't have the same high level as the exterior of the spacecraft, but it's cleaned. As Chris McKay would point out, a NASA Ames astrobiologist, it doesn't mean we're not sending something up there. There's no such thing as zero. That's sterilization to the zero level. But on a spacecraft, 300,000 spores is all that's allowed on a huge spacecraft. So it's cleaned to a very, very high level of cleanliness. It's maintained that way during launch, and those figures are given to the UN, to COSPAR, Committee on Space Research. So the UN has that data. We know what's gone up there, so we can even account for false positives. But have we sent microbes to Mars? Yes.
Hi, my name is Lupi Fernandez. I'm a writer. My question is to Margaret. What about other countries? Would other countries also observe this very rigorous quarantine procedures, or even amateur efforts? You know, even if they're American, but
There haven't been any amateur efforts, but the UN Outer Space Treaty, which has over 100 signatories, and it's one of the largest. The UN Committee on the Peaceful Uses of Outer Space is one of the largest committees in the UN. As far as we know, all the launching nations so far have maintained planetary protection control. There's some questions about whether the Russian spacecraft might have been as clean as we thought. While the scientists made sure that they were put together clean, their methods might have been different than ours. We use one method of cleaning, they might use another. They give their spacecraft over to the military, or did at that time, so whether or not it was totally clean when it went is, you know, if people had champagne parties around the rocket before launch time, which some said they did, then it wasn't as clean as ours might have been. But the nations that are launching right now, and any partners, definitely keep track of planetary protection.
And that includes China.
Yes, and so the thing is, it's one of these where it is all kind of self-governance. It's everyone says, I'll do it right, and there's no way of checking.
Thank you.
Which is a question that we have as we go forward to commercial. How do you do it? Also, commercial would be subject to all these same regulations because the treaty says launching nations who signed are responsible for overseeing what goes on from their nation, whether it's government or non-government entities. So commercial will be subject to it at some level.
I guess just to add a little bit briefly on this, is a little bit of a safety built in, is that the surface of Mars actually is very sterilizing. So it's the same problem that you have in the panspermia. There's so much high UV radiation that everything that's on the surface would be sterile after a while. But as in the panspermia problem, I think, and Margaret can confirm that, if there are any spores that are within the spacecraft, those would be more protected from radiation. But, you know, there is also the sterility on the surface of Mars.
And the digging. Any sample implements that you use to dig, as Dale well knows, you know, you can go and have everything be really fine, but if you dig with a dirty tool or you don't know what's on it, then you're contaminating your own samples.
Right. There's actually two reasons why you want to do that. You don't want, if you've got a life detection instrument, or if you're looking for organics or something, you don't want to discover things that you've taken with you. So you want it to be ultra clean. So that's actually pushing on that cleanliness as well. And then anything that touches the surface has to undergo, as Margaret said, an additional set of quarantine or set of cleanliness standards that are very, very rigorous.
Well, in fact, there was an article 2 days ago, I think, that NASA discovered that there was some Teflon around the drill bit that the Mars lab is using, and that they would discover carbon.
That's right.
Yeah, but
Teflon
you
is
see-
made of carbon and a little bit of fluoride. Thank God for the fluoride. That would say, okay, that's us.
Yeah, well, see, that's not a planetary protection issue. That is not a concern about a contamination that would be a biological contamination for aliens. That's a science issue.
Science issue.
And so those two are separate. So the Planetary Protection Office worries about things that would be replicating. And anything else is, you want to send a lousy science experiment up there, it's your problem.
The gentleman at the back, you've been patient.
That's okay. My name is Andrew Masika, and I was trying to think of a more contemporary example, and I might have the mission name incorrect. Stardust, where we went out to try to get some samples of a comet.
Right.
So the thing that goes through my mind is, what were some of the considerations, the history, and the engineering precautions that were done specifically for that mission?
Okay, so Stardust was a mission that flew through the tail of a comet, and they had this almost like tennis racket thing that came up, and as it flew through, it collected particles in aerogel. So number one, the particle sizes are really, really tiny. It's not like being inside of a rock. So the probability that something might be up there that was biological and could exist and persist is very, very low. So number one. In addition, the way it was collected in the aerogel, you got a flash. It slows down really fast, and that gives it momentary heating. That heating was essential of kind of sterilization. And the third thing is, nobody is expecting that in the tail of a comet that's coming up by in space that you'd have anything that would be able to live, even if there were something in there. So that question of, surviving radiation and all that. So collecting something from the tail of a comet does not have the same planetary protection requirements and stringency. They did have to file a planetary protection plan, but that was it. So when it came in, it just crashed back into Earth, and we picked it up. And
The bigger concern was actually contaminating the samples from Earth.
That's right. That's right.
Doug?
Yes, Doug Flegel. Do you have a mic? Yes. Your question is about human flight to Mars. Clearly, if you go to Mars, we each have 100 trillion microbes on our bodies, so it'd be tough to get it down to 300,000.
Actually, trillions.
100 trillion.
Yeah.
What would be the policy considerations about how much robotic exploration would have to be done, how much identification of potential life on Mars, so that, it would be a big step. If you're sending a human, then is the game over as far as protecting Mars from outside biological contamination?
Okay. Yes and no. It's just like these guys can go out into their field sites and do their research and do very good research, even though they are bringing along all their microbes. So we can control the amount of contamination that's out there. We can sample things in aseptic ways. But you're right that it doesn't take I'm not a microbiologist, doesn't take a microbiologist to sit down and think about what kind of hypothetical situations and concerns you have. And so this is precisely the kinds of questions that are being asked all the time. What would it mean if we go with humans? Does that mean we've avoided all of the planetary protection considerations? Would that be harmful contamination? Those are the questions that are being asked now. The first set of guidelines that came out of the Committee for Space Research said basically when we go with humans, we have to think about three things: protecting Mars from hitchhikers, protecting our astronauts, of course, and protecting Earth. But protecting Earth is the primary consideration. Those detailed protocols have not been set. Obviously, we don't have any human missions yet, but the guidelines and the principles are there, and they too will go through this incremental review.
Okay, quick follow-up then. So would it be that the best way to protect Earth would be to make all trips to Mars one way? No, I'm not joking.
Not joking.
This is really serious.
Well, the best way is to don't even go. Then you don't have any planetary protection problems, right? So this is something, when you do an environmental impact statement, you have to include the null alternative. What if you do nothing? Great, you don't contaminate Mars, you don't contaminate Earth. But is that what we want? So you're right. One-way missions would do it, but then you come into other questions that are ethical and involve theologians and others? What if we find life up there that is biochemically distinct? Does that make it a, quote, second Genesis in lowercase? And how does that deal with theologians? What do theologians and various religions of the world think? And the good news is that we are actually talking with folks. For the mainstream religions, all the Judeo-Christian religions, which all the Abrahamic traditions, which include Judaism, Muslim, anything that's biblical, no problem. God created the heavens and earth, and it is good. And so we're talking about what it would mean ethically, too. So the one-way mission is not a concern about planetary protection as much as it is about ethics, and that's not science.
We have a young woman at the back, please.
Okay, so my question is that, so things that are going to other planets have to be rigorously cleaned, but do things that are just going to space general have to be cleaned? Like things like Voyager?
I can't hear. Could you lower the mic to your
yeah.
mouth?
Did you say like moisture?
No, Voyager, I think.
Oh, Voyager. Oh,
Outer-
okay.
Outer solar system.
Oh, okay. So it depends where you're going. So if you're going to the sun or to Venus that's really, really hot, you know that nothing could survive from Earth. So you don't have the same level of planetary protection. Likewise, people tend to say outer space and they think of everything. We don't clean the shuttles when they go. We don't clean anything that's on the satellites that go. They're on Earth orbit, and that's not a concern. Earth is Earth. Earth and moon now, we know. So we're talking the moon and beyond. And so spacecraft that are going to land are have stricter controls than spacecraft that are going to fly by or keep going. So Voyager probably has contaminants on it, but it never landed any place, and it's just going. And so whether anything is still alive now after all those years in space, I don't know.
Margaret, but maybe you could comment on putting something in orbit around something like Europa or
Oh,
Titan,
okay.
and
So-
what the policies are involved with a spacecraft circling something like that.
Okay, so when you're thinking about a moon of other planets, like so Europa, which is a moon of Jupiter, if you send something up there, the question is, so Europa is the one with the icy crust and the ocean underneath, and the real concern is if you send a spacecraft up there and it's orbiting, eventually it will come down. And so that means you'll have an RTG, a radioactive heat source, that could melt through. How far could it melt through that ice? Would it get entrained or trapped someplace down in the ice, or would it go all the way through? So one of the things we don't want to do is contaminate a place like Europa or Enceladus. So when the planetary protection controls are put on a mission, it also includes steps at the end of the mission. So for instance, on the Galileo, which went to Jupiter, at the end of the mission, because there might be some probability that over the time that it's just still up there as an orbiting spacecraft, out of control, that it could crash into Europa. They had it crash into Jupiter instead. They deliberately crashed it into Jupiter so it could not crash into Europa. So planetary protection also includes operational constraints. So they say, you know, don't go near there, or prove to me by calculations that your orbit will stay up a certain amount of time. But all these things will eventually come down someplace.
Terry?
Yes, that is me. Thank you. As someone who supplied equipment and worked with biotechnology companies in the early days of that business, your comments about not wanting to contaminate the sample or let the sample contaminate us is identical to what that whole industry does. To what extent do you collaborate with those people in exchange of technology?
Extensively collaborate with people from other industries. And in fact, it was the Viking missions to Mars in the 70s, and there were tremendous amount of exchanges with all the people in biological industries working on sterilization. So electronics clean rooms and biological clean rooms, and think surgical. The problem that we have is in some cases something like, so surgical and hospitals, they use autoclave, that's dry heat, temperature and, not dry heat, it's steam. And so you've got moisture, and that doesn't work really well with your electronics. So we tried to look at what it is electronic industries do, what the other clean rooms do. So that's what goes on behind the scenes, is all of that kind of research.
Sir?
Yeah, hi. There was a case, a famous case a number of years ago, where there was the red rain in India that people were thinking was blood falling from the sky. And of course, the botanists in India identified it right away as being stratospheric spores of some algae, but still to this day, it's often thought of in the media as being a case of panspermia, some sort of red germ that came from outer space. Have there been any other cases like that where there's a popular misconception or even a fringe scientific belief or something that we've got here where some number of people believe that it comes from outer space somewhere?
Go for it.
Other things?
I think the only thing that comes to my mind is, sometimes you do get reports of meteorites that have evidence of life inside them. And of course, most of those are just not credible reports. It's all, when you look at it more carefully, you find that it's just earth contaminants that have been found inside them. But there's still lots of reports online about life in meteorites and how they've been collected and what does that tell us. But I wouldn't bet the farm on it.
Right.
Well, I would bet what happens too is that we go to people like Dale and Alana and ask about extremophile biology. The first thing you have to ask is, could it be something that's already here? Could it be a contaminant? Could it be another form of life? And so that's why all the astrobiology and the extremophile analogs that we do on Earth are so important. Because you first have to say that. And some people would even say that panspermia is a far-out hypothesis. Some scientists just say, no way.
Grant?
In case of a worst case scenario where the bacteria are brought back to Earth and there's maybe a smallpox infection from this outer space bacteria, where are the protocols for handling that, or are there any if we were to bring back a smallpox from Mars?
I would ask too, do these guys have, when you do your field work, do you have any protocols or any permits that you have to get for what kind of samples you're bringing back?
With things that I do, no, there are no protocols on samples and restrictions. The only restriction is, like you were saying before, is rocks in between countries and things like that. You don't want to bring anything that's not endogenous here. But your question is actually going past that, right? You've already brought the thing back. How do you deal with it? And I think that's where a lot of learning comes in. It's the containment that Margaret was talking about. Containment is really, really important, but also be able to actually access the samples. So we have in my own lab, we're only up to BSL2 for the biosafety level 2. But it really comes down to containment and what you do next. And how you protect yourself. So there are many, many steps. There's not just one. So hopefully you won't get to the place of an infection. If it's a larger infection, you have to contain a larger population. Gets back to the quarantine, right?
Yeah. Well, the one thing too is when we bring something back, it's fully contained. We're talking about, for Mars in particular, we're talking about bringing 500 grams. That would fit in a coffee cup. So we're talking about bringing back very little. We're talking about putting it into a containment. It would be so valuable scientifically that it isn't going anyplace real soon. It won't be like moon rocks going around to museums, I don't think. There probably would be too little of it. In addition, chances of finding something like smallpox are very little. Think about smallpox needs a host. So smallpox by itself doesn't mean anything. It's only when it gets inside of you. We can't even find life up there. What's the chances you're going to have a pathogen and a host? Very, very low. So you can go through all of those arguments, but then in the end, too, if you bring it back and it has a biology that's based on carbon or any other chemistry that we know, if we found life, probably would just seal it up in the glove box and stop and think about it. Or if you really wanted to get rid of it, you cook it. You break all the chemical bonds. You turn it into charcoal. So bringing something back is not a scary thing, because we're doing all the protocols. And again, we work with Center for Disease Control and others, and we're taking the step of putting it in biosafety level 4, the maximum containment that exists, not because we think there's life in it, but only because we don't know. And that's how CDC does it. If they don't know about something, they put it in biocontainment 4, then do a series of tests on known organisms and look for biological interactivity and such. And if it's okay, then they drop it down to 3 and then to 2. So the AIDS virus, for instance, is handled at a level 2. So these things they're very, very well set and studied, and the things that we have on Earth are far worse. And just because there's smallpox or Ebola or something else on the planet doesn't mean that it's killing us here in Santa Clara.
Yeah, I think it's important that people should understand that, you know, diseases have had billions of years to co-evolve with other organisms, and that evolution, that co-evolution, is really important in how they can use their biochemistry to take advantage of our biochemistry. So it's not something that may just happen naturally, you know, with a foreign organism if we ever find it.
And I think what I want to follow up on what Dale said, because I think it's really, really important. As a biologist, you always look at not at the steady state, but the evolution. And so you did find alien life, and you would coexist for a while. I mean, we tend to think as humans that we're going to be stuck in time, and we're going to be exactly the same way, the way, you know, in 10 million years from now, the way we're now. And it's very unlikely. And there's nothing scary about it, about evolving, right? I'm not saying that, we should allow interaction with alien life or not protect ourselves from extreme biology, but should we find it, and if at some point it would coexist, it would happen probably exactly what Dale says, there will be a co-evolution. And I think, and part of the thing that's it's in the media and a lot in human consciousness is that, what's happening with the humans? We evolve. I mean, we look back in our own history and we evolve, and it's okay.
Yeah, the second half of this, the title of this talk is Protecting the Planet from Extreme Biology, and what keeps me up at night a little bit more than being infected from Mars is the fact that we are starting to redesign bugs here that could make them a heck of a lot more dangerous than anything else we can imagine. You're going to ask a question, and after that I would like each of you to tell me what is your what was the evolution of your thinking of the happenstance of life in the solar system or outside based on your own career? What did you think before? What do you think now? Ma'am?
Hi, I wanted to step it up a couple of tens of thousands of feet to a policy level question. I'm a biotech patent attorney, and I have encountered policy issues in education at the national level with respect to those kinds of issues and political fears of what the scientists will do. Recently, Paul Krugman made a half-joking comment on CNN about proposing that they have credible evidence of an alien invasion coming in order to stimulate the economy. And one of the, to build infrastructure to deal with this, starting with high-speed rail and everything else. Yes. One of the themes of this conference has been the poor funding of this kind of basic research that you guys do, and yet, which we all know has practical implications between Tang and Velcro and everything else. It has very good commercial applications as well. How far do you think is reasonable to, let's just use the word exploit, the public fears of alien invasions and contaminations and exobiology issues to generate funding that really is for a good purpose, but the ethics behind it might be a little political?
I guess my first reaction would be always tell the truth.
Yeah.
Knowledge isn't something that we should avoid. I mean, it's something that we should embrace. And science is just that. It's seeking the truth. It's not a political equation. It's just this is the answer. So policies can be developed from those answers. But yeah, I just think people should just understand. And I think the hardest part is people, sort of the educational level. Some of these are complex issues, and if you don't have the fundamental understandings that help you wade through this morass of information, it's difficult for the average person to understand what the hell's going on, and how do you make decisions out of that, and how do you trust the people, and so it's I think the truth is the most important thing. Shedding light on the truth all the time.
Yeah, And I'm happy you asked that question, because that is really important in the social factor that we're talking about the fear, right? And I think nothing justifies manipulating people that way. Because in fact, it gets back to what Dale was saying, it's not building trust. What you need to do in order to be able to do this is build trust. And the one way to build trust is real knowledge. So I think a better option, it's not that we shouldn't promote science and should find finding the better option rather than manipulating people's fears is educating them to know what's real, what's the truth. And then the fear goes away.
Yeah, and I would say that I've heard some of those same arguments talked about since 9/11 and the anthrax scares that followed right after that. So the government mounted a huge buildup of biocontainment labs, the biosafety 3 and 4 labs. Before there were 2. There was one at Center for Disease Control for civilian things, and one at USAMRIID had one, and then there was a biosafety level 3 out in Utah that was a Air Force, but biomedical and the Army, looking at how do we protect our troops from biological warfare, so defensively, not offensively. So some suggested we don't need all those labs. On the other hand, with all of the concern about infectious diseases and flus and things like that and pandemics, they are labs that we do need. But there are some suggesting that a lot of biotech and biomedical people went that way. They didn't have their research in that, but you switched to a different disease and now you can get funding. So I understand that fully. The good news for us is that's not what's happening here. I'm much more in the case of if we're going to bring it back, we need to do it right. And so we have a chance to learn from all those biomedical labs and everybody else. And it's a matter of civics. It really comes down to how your science is played out in a democracy. And while some people are really, really big on wanting to go into space or to spend the money on on exploration, what we're doing is basic science. And this is a matter of priorities within a country or any country. And so I'm doing basic science, and if we decide that it's more important to put our money towards food or energy or something like that, that's a congressional issue. It has nothing to do with the science that I do. And what I have seen is within the space community, there's been very responsible research exploration of the issues, and they're saying, if we go, let's do it right. And I have been really, really pleased as a citizen watching how NASA does it and the science community saying, if we're going to do it, how would the best way be a way to do it? And then where's the education behind it? Where's the facts and the information? So I use this all the time when I go to classrooms and talk to students about this is science in the real world. And whether you're a patent attorney or a rocket scientist or a biologist, there's a role for all of us to play.
Dale, maybe you want to start by describing the arc that the evolution of your own thinking about life in the solar system.
I guess since I've started working in this area, I've just become very hopeful that we're going to find additional life in our solar system. I think the evidence is very good that Earth and Mars shared similar histories early on, and that if life originated there or if it originated here and was moved back and forth, that we might find evidence of that life. And now that we've come to a greater understanding that there's probably liquid water in the oceans off of Europa or beneath the ice of Europa and Enceladus, that gives us hope. And it's exciting to understand whether or not that life is like us or if it's a completely different route and different evolution of life. Maybe it's just totally different from us. And that would absolutely be totally cool, because that would give us a lot more hope for finding common life throughout the universe.
I like that question you asked about the evolution of personal thoughts towards synthetic biology. And I had this experience when I went in 2007 at a conference called A Conference on Mars. And there was an email thread that went around with all the scientists from a person that asked the question, well, why don't we just take all the mechanisms that Deinococcus radiodurans, which is a bacterium that's extremely resistant to radiation, to 1,000 times more radiation than humans, and transfer all those mechanisms to humans? Should be easy, right? And it almost made me laugh at the time, because Deinococcus radiodurans is famous for, its fast DNA repair, but it's a really extremely complicated mechanism. And there's really no way you could transfer this information from a bacterium to a human. There's, cloning and transgenics and all sorts of complicated things. And, people shot off ideas and speculation about antibodies and whatnot. Well, this was 2007, we're in 2012, and as it turns out, the mechanism of resistance of Deinococcus radiodurans to radiation implies something very simple, which is its protection of its proteins by manganese. So now there's this whole shift in the community. Everyone is looking at manganese bacteria and how can manganese, protect everyone from anyone else, and can we make humans with manganese, whatever. The point is, biology and science are evolving. And synthetic biology is very powerful, but it's like everything else in evolution, you have to take it in small steps. I think it's very unreasonable to say, I'm going to take something from, at least in 2012 right now, it's unreasonable to say I'm going to take something from a bacterium and move it in humans and be all happy with it. Because even if the molecular mechanism is identical, the physiological endpoint will be very, very different, right? So that's on an evolutionary scale. But what we can do is maybe think small step and take things from a bacteria and move it into an alga that may produce food for astronauts to go on the moon or something like that. So you can take it in small steps and see if these mechanisms are adaptable. But it really comes down to the evolution of life and the fact that we all have and share the same biochemistry. And there's wonderful work, of course, by Craig Venter, who's done all this synthetic biology. And it comes back to what Margaret was saying. For example, at NASA Ames, there's this whole initiative of synthetic biology. But it comes, what I really like what Margaret's approach is to really work with what else is in the community. So the space exploration, I think this points to the synthetic biology into space exploration points to the fact that we're no longer, just one agency doing one thing. And in fact, the science that we do at NASA or the exploration that we do through all the space agency takes advantage of the entire knowledge on the entire planet, and I think that's really cool.
My evolution went from, as I said, mud snails to something that I never planned. So initially it was this idea of environmental impact. What's the impact of organisms and how do communities work? Then it went to how do you take the information and make sure you're being careful. So how do you think about the release of a genetically engineered organism or the return of something from space? And what it's gone on to mean for me is this wide appreciation of the need for lawyers and mass media and all different careers and backgrounds, because we're all in this together. And so it's a real strong feeling about education. So I'm very involved in science education and love to talk to kids about, what's your passion? If your passion is running or skiing or something, there's science behind that. Who made ski bindings so that we don't break our legs like we used to? So anything that you like, I can turn that into science. And the other thing is the notion of responsible citizenship. So, and the final one is, so it doesn't just happen. It's because people take the basic information, think about what the implications are, and then work it out in the real world. And the final one is, despite all of the wonderful talk about 100-year starships and going to other planets, we have a tough time planning missions. It would be very expensive to go to Mars with 5 or 6 people. So what it's done to me as an ecologist is really think a lot about sustainability on this planet. I think on a planetary scale, and I think about this is the one we've got. And maybe we can think about evolution and what our populations will be like, millennia from now. But in the meantime, I care about me and my family and my community. So sustainability and taking care of this planet is the key. And education's a part of that.
I just wanted to add one thing before we're out of here, and I would encourage all of you, if you're interested in planetary protection, just to key those words into Google, and you'll find the Planetary Protection officer's webpage from NASA, and there's just a wealth of information there. For example, there's an ebook that came out about 1.5 years, 2 years ago called When Biospheres Collide, and you can download that book. It's very easy to do. It's got a history of a lot of the things that you've heard about today and talks about some of these issues. And there's the actual guidelines from COSPAR. You can download them right down there and see what they're all about.
Yeah, and NASA's a civilian agency, so all of this, some people will say, I know you can't tell me. I can tell you anything. Yeah. This is all wide open, and that's the beauty of it. So you're asking basic questions from deserts and Antarctica and you name the habitat, and just building on the concepts we all learned in high school.
Well, with that, I want to thank the panel and certainly you also for joining us today. Thank you very much indeed.